Good morning. I am Dr. Archana Kushwaha. I am working as an assistant professor in Institute of Aeronautical Engineering College. Here today I am going to deliver a lecture based on the engineering materials, and the topic is the introduction of polymer. So before going to the introduction of polymer, first we should know what is the meaning of the material engineering or material science. So material engineering or material science is an interdisciplinary field that deals with the properties of a material and its application to a number of areas of science and engineering. And coming to the polymers, polymers are a high molecular weight an organic compound in which a large number of a simple unit repeat themselves in a fixed pattern. So, high molecular weight itself, it is a meaning that it contains a high molecular weight, and organic compound itself, it is a meaning it will made by the organic compounds. Organic compounds means it will contain carbon, hydrogen, and nitrogen or oxygen. So, for example, CH4, a simple molecule of an organic compound is a methane, that is a CH4, C6H12O6, that is a glucose. These all are the example of the organic compounds. Polymers are widely used advanced material which are found almost in every material used in our daily life. Even though we are totally surrounded with the polymer, whatever we are using, whether it is a pen or specs also, which I am using right now, these all are made up of the polymer, and our body is also made up of natural polymer. For example, DNA, RNA, cellulose, etc. Now, coming to the extensive use of polymer, why it is that much important? Because of these much properties of the polymer. For example, most of the polymer are non-toxic and safe to use. So it is so that is why we are totally surrounded with the polymer. It has a low density, that is light and light in weight, so that is why transportation of the polymer is also very easy, and it possesses a good mechanical strength, resistant towards the corrosion, so that is why it will never absorb the moisture when exposed to the atmosphere, work as a good thermal and electrical insulator, and it can be molded and fabricate easily. It possesses aesthetic color. Here I have given some pictures of the polymers which we are using in our daily life, like cosmetics, fertilizers, paints, rubbers, fabrics, plastics, etc. In the definition we have used, like, it will made up of large number of a simple unit repeat themselves in a fixed pattern. So that simple unit will is known as the monomer, and here it is very important that monomer should be true monomer. True monomer itself, it is a meaning that at least it should contain two functionality. Functionality, true monomers means it contains at least two functionality, and functionality or bonding sites, it is a meaning like that molecule, it should contain at least two bonding sites. For example, here if I would say that CH2 ethene molecule I am talking about, here we can see this is the one compound which has two functionality. Two functionality means there are two bonding site where two types of other molecule it can bind. For example, if we will go with the example of ethylene, here we are making that a polyethylene. So whenever we are taking that ethylene, so it contains that two functionality by which they are connecting with the repeating unit of a CH2, single bond CH2, so which is known as a functionality. So that is why we should totally understand that while preparation of polymer, that monomer should be true monomer. And there is a difference between the functionality and functional group. Functional group meaning like here I have written CH3OH. In methanol, that OH group, it is a one functional group, and functionality means the one single bond which we can replace some other molecule in the place of OH group. So that is why in CH3OH there is only one functional group and one functionality. While in ethylene group, here one functional group, so double bond itself, it will be come under the functional group, and here there is a two bonding side. That is why here two functionality is there. That is why this will be comes under the true monomer, while CH3OH it will not be the true monomer. Here also in that third example, that the two OH group, it shows like a two functional group, while we are attaching any other group on the place of OH group, it will show that two functionality as well. So these two will be the true monomer, while this will not be the true monomer. So the polymer are very vital, and one cannot imagine our life without polymer. Since polymer a is a large class of a material which consists of a many small molecules named monomer, which I have already said in a previous lecture, like that a large number of a simple unit, that simple unit which is known as a monomer, and it should be true monomer, which will contain that formation of a polymer. So polymer, a large class of a material, consists of a many small molecules named monomer. Monomers one, and mer means part. So one part will be repeated together and it will form the polymers. Polymers many, mer means parts. So it will form polymer. That is known as a polymer. So small molecules names monomer that are linked together to form a long chain and are used in a lot of products and goods that we are using in our daily life. Here, which I have already mentioned, that the meaning of the polymer. Now it come to the some natural polymer also. It is also interesting to note that many carbohydrate, proteins and enzymes, DNA, RNA are the natural polymer, and the word polymer, sometimes it is known as a macromolecules, is derived from the classical Greek words, and the meaning of the poly means many and mer means the part. So I have already discussed previously. So the polymer molecule has a very high molecular weight, and it is a range of 10 raised to power 4 to the 10 to the power 7 gram per mole, and it consists of a several structural units usually bound together by the covalent bond. For example, polythene, as I have said earlier, that here n number of the molecule is there in ethylene group, and after the polymerization process, it will form the polyethylene. Here, two functionality is there. That is why it is a true monomer. Uh, that is why it bound together and form a polymer, that is a polyethylene. Thus, the repeated unit of the polymer is called as a monomer, and the monomer repeating unit is a polymer is called as a degree of polymerization. For example, here in case of ethylene, if n number of the molecule I am taking to make a polyethylene, so n itself, it is the meaning is the n is the degree of polymerization to form the polyethylene. So, for example, if 100 molecule of ethylene polymerize to give a polymer chain, the degree of polymerization is 100. Now coming to the types of polymer. Here I have explained four types of polymer. That classification is based on one classification is based on the origin of polymer, which is further subdivided into the natural polymer, semi-synthetic polymer and synthetic polymer. And second was the based upon the structure of polymer. Third one is based on mode of polymerization, and the fourth one is based on molecular forces. Now coming to the first part, that is a classification based on the origin of a polymer. Here, three types of polymer are there. First is natural polymer. Natural, as I have said earlier, natural polymer which is already formed in the by nature. For example, the polymer cultivated from the nature are called as a natural polymer. They are fabricated in plants, animals, and are vertebrally involuntary for the life. For example, protein, cellulose, starch, nucleic acid, natural rubber, etc. And our body is made up of the natural polymer, that is nucleic acid, starch, cellulose, protein, etc. Now coming to the second part, that is a semi-synthetic polymer. Semi itself, it is a part of the natural polymer, and uh, further change of further change in any natural polymer, it will comes under the semi-synthetic polymer. For example, okay, giving the coming to the definition, these polymers are frequently deduced from the naturally coming about polymer by chemical differences. For example, as I have said, if I will change in something in natural polymer, it will comes under the semi-synthetic polymer. For example, cellulose is natural polymer. So, if cellulose is a natural polymer, on acetylation with acetic anhydride in the presence of a sulfuric acid, cellulose forms a cellulose diacetic polymer, diacetic diacetate polymer, and this will known as the semi-synthetic polymer because it is made up of cellulose, which is a natural polymer, and further change in cellulose by acetic anhydride and sulfuric acid, it will change as a cellulose diacetate polymer, that is known as a semi-synthetic polymer. It is used in fabricating threads, threads and material like films, glasses, etc. Other examples of semi-synthetic polymers are vulcanized rubber, gun cotton, etc. Now coming to the third part, that is a synthetic polymers. Synthetic polymers, which is also known as a man-made polymer. This is purely made in laboratory only. For example, polyethylene is the best example of the synthetic polymer, which is made up of the ethylene molecule, and which we are very extensively we are using as a polythene. The polymers grown in the laboratory are called as a synthetic polymer. For example, polythene, Buna asp, polyvinyl chloride, nylon, etc. Now coming to the second classification, that is a classification based upon structures of polymers, and they are further classified into three parts, that is a linear polymer, branched chain polymer, and cross-linked, or sometimes it is known as a network polymers. Linear polymers, as we can see in the structure, linear polymers, it will be sometimes it is also known as a straight polymer as well. So it will connected with different it will connected with the monomer in a single chain, like so it will form like a linear polymers. These are the polymer in which monomeric units are correlated concurrently or to crystallize long and linear chains. These direct polymer are well packed. These are the well packed and thus hold a high density. This is a very important point. So that is it holds a high density, high tensile strength. Tensile strength, that is if we will stretch, it will further change their to initial shape, and high melting points. So, some common examples of the linear polymers are high density polymer, which we are very extensively we are using. For example, whatever the packing of the food material, it is especially high density polyethylene. This is also known as HDPE. Bread packaging, biscuit packaging, these all are the HDPE. Polyvinyl chloride. Polyvinyl chloride is also very extensively used, but it is not used for the food packaging since it is somehow toxic also. Nylons, polyester, etc. Coming to the second part, that is a branched chain polymer. Branched itself, it is a meaning that some branching in the linear chain it will be there, then it will comes under the branched chain polymer. For example, if I will say about this blue line, that will like a linear polymer, and there is a green line that shows like a some branching is there. That is why we known as a branched chain polymer. These are the polymer in which monomer are combined to form long chain that have side chain. That is the main point, that have a side chain or branches of a varying length. A varying length itself, it is a meaning that branches will not be the same as always. Like here, two carbon molecule is there. So if I am saying that this green is showing that carbon, so it is contain the two carbon. Here it is contain three carbon molecule. So that branches, it is not always consistent. It will be varying length also. These branch chain polymer are packed irregularly. Why irregularly? Because there is a no sequence of branching in the branch chain polymer. Therefore, have a low tensile strength and melting point than the linear polymer. Some common example of the branched chain polymer is a low density polyethylene, that is LDPE, glycol, starch, etc. Now coming to the third part, that is a cross-linked or a network polymers. Cross-linked, this is the example of a cross-linked and a network polymer. These are the polymer in which monomer unit are cross-linked together in a three-dimensional network. These are also called as three-dimensional network. Here, if I suppose to explain the cross-linked, here if I would say this is the linear polymer, this is the second chain of a linear polymer, if it will join together. And one more thing, if we would say about the cross-link, we have to say like in a cross-link polymer, there will be the more than two or equal to two functionality. Functionality itself, it is a meaning binding site, as I said earlier. So in this, if binding site will be more than two, then it will comes under the cross-linked or network. Cross-linked and a network polymer. Because of more than two functionality, they are binding from each chain to the other chain. Here, like other chain, these type of bonding will be there, and that bonding will be covalent bonding only. If that type of bonding will be there, it will comes under the cross-linked or a network polymer. These are also called as a 3D work modes. These polymer are a rigid, brittle due to the network structure. For example, bakelite and melamine, it is a very good example of the cross-linked polymers. Now coming to the classification based on mode of polymerization. Here uh, uh, that classification, it will be again classification based on the mode of polymerization, which is further subdivided into the two parts, that is the and addition polymer and condensation polymers. Now coming to the addition polymer itself, it is a meaning of polymer formed by the lump sum addition. Lump sum addition means whatever we are taking as a monomer, the polymer means the molecular weight will be almost equivalent. Means if n number of molecules I am taking as a monomer, so n number of a polymer that molecular weight will be formed. So that will known as a addition molecule, addition polymer. Lump sum addition of a repeated monomer to end product molecule is called as a addition polymer. That is, in addition polymer are formed by adding monomers unit without any loss of atom. If any loss of atom will not be there, then the whatever we are taking as a molecular weight of a monomer, that will we will get as a polymer. So any loss of atom or group will not be there. That will known as the addition polymer. These are the formed by the repeated addition of a monomer molecule possessing double bond or triple bond. For addition molecule, this is the mandatory, like a monomer should have a double bond or triple bond. Otherwise, it never form. It will never form. For example, polyethylene is formed by the ethene. These are the again for classified as a homopolymer and a copolymer. Homo means same, co means different. So, if same type of monomer combined together or joined together, it will form the polymer which is known as a homopolymer. For example, here I am taking the A type of molecule. A is a single monomer which is combined together and form like a like that. So that polymer will comes under the homopolymer, because here we have taken only single type of monomer. That is why it is known as a homopolymer. So definition: these polymers are formed by the polymerization of a single monomeric species. For example, formation of a polyethylene, we are using only ethene molecule as a monomer, CH2 double bond CH2. So it will known as, it will be like that, because it is showing that it has a two functionality. Now coming to the copolymer. Cop means different. Copolymer, that is, these polymers are formed by the polymerization of a two different monomer. For example, formation of Buna S from styrene and buta 1,3-diene. If two types of molecule will be there and it will there by through during the process of a polymerization, there will not be any loss of the molecule. It will known as a copolymerization of addition polymer. For example, here we have given the example 1,3-butadiene. This is, and this is styrene. Here that Buna as it is formed. Here double bond is mandatory because it is a addition polymer. Some common addition polymer example is a polystyrene, Teflon, Buna S, PVC, polythene. These all are the example of addition polymer. But here that Buna S will be the example of addition copolymer. There is the example of a addition copolymer, like here two types of different monomer it is there, A and B, and they are repeated like this manner, then it will comes under the addition copolymer. Now second is a condensation polymer. Condensation polymer itself, it is a meaning that two different type of molecule come together and condensed, and after uh, is- after a loss of some molecule, it will form the condensation polymer. For example, the definition is a polymer formed by the condensation of a two or more like or unlike monomers with the removal of a simple molecules. In the condensation polymer, that removal of some molecule like H2O, HCl, ammonia, etc., it will be there, then it will comes under the condensation polymer, such as water, alcohol, ammonia, HCl, etc. It is called as condensation polymer. For example, nylon 6,6. This is the nylon 6,6 structure. It is formed by the hexamethylene diamine and adipic acid. So if we will see here, here is the OH group, which is a leaving group, and here is H. By coming together, the loss of the water molecule, it is formed the nylon 6,6. Here that is 6 itself, it is a meaning that number of carbon. In adipic acid, 4 carbon is there, 5 and 6. So 6, and here in hexamethylene diamine, this is also a 6 carbon. That is why we known as a nylon 6,6, and it is a condensation polymer. Now coming to the one more example, that is a nylon 6. This is not the condensation polymer. Why? Because here there is a no loss of any molecule. So that is why it will comes under the homopolymer. But this is also not the addition polymer, or we can say addition polymer, but this is a special type of addition polymer, since here there is a ring opening process is there. That is why we can say that addition ring opening polymer. So it is nylon 6. It is formed by the caprolactam. Here there is a no loss of any molecule, only that ring opening process is there. That is why there is a no multiple bond also. While in addition polymer, what we are saying, that multiple bond, it is mandatory, whether it will be double bond or triple bond. But in caprolactam, this is the special type of bonding where there is a no multiple bond and there is a no condensation polymer also, means there is a no loss of any molecule. That is why it will comes under the special type of polymer. There are some differences between the condensation and addition polymer. Many of the things already I have said earlier. For example, it is known as a, yes, of course, this is a step growth polymerization. Step growth polymerization, like condensation, we are taking A type, B type molecule, further together A, B form, then AB. Here, for example, what I am saying, that adipic acid and hexamethylene diamine, that will condense together one molecule. This molecule is formed, and this itself, it will use as a monomer for a further polymerization. This is different molecule which is condensed together and form a molecule which is a different type of monomer, and that different type of monomer, that repeating different type of monomer, it will form that condensed polymer. So here this is known as a step growth polymerization, while this addition polymer is a chain growth polymer. Here only we are taking like a type of molecule, it is formed. It is formed like a AAA type. This type of polymer, which is known as a addition polymer. It takes place in monomer having reactive functional group. Here functional group is mandatory. If functional group will not be there, then there will not be any loss of molecule. So just because of loss of molecule is there, it should be there. So functional group, reactive functional group should be there in condensation polymerization. While in the addition polymer, it should contain multiple bonds only. It takes place with the elimination of a simple molecule, which I have already said earlier, that is like a water molecule, ammonia, HCl, etc. It takes place without elimination of a simple molecule. That is why we are saying lump sum of a molecule will form in the polymerization. That means N type of CH2 double bond CH2 we are taking after the polymerization process. CH2, this is a single bond, because that is for that is why we are connecting together ethylene molecule, because of their two functionality. So what are the molecular weight will be, suppose that molecular weight will be here M1 and here it is a M2. So M1 will be nearly equal to the M2 only, or maybe it will be approximate same. Here, that repeating unit of a monomer will be different. As I have said earlier, in the formation of nylon 6,6, what we are taking, that adipic acid. Suppose adipic acid, it is a and hexamethylene diamine, it is a B. This is the different molecule which combine together, and after some loss of molecule, like suppose minus H2O, that AB formation is there. This AB will work as a monomer in condensation polymerization. So this is not the proper polymerization molecule. Here this will work as a further single monomer which is combined together and form that polymer. And here in case of addition polymer, repeating unit and monomer will be same. For why? Here I have explained CH2 double bond CH2. This is the monomer of a polyethylene, and in the polyethylene, that is the formation CH2 single bond CH2 and type of the molecule, it is a combined together. So monomer and repeating unit are the same, and the polymer is formed in gradual steps. Reaction is a fast and polymer is formed it at once only. Why gradual steps? I have already mentioned. Here in the case of AB, this will work as a further for the polymerization, which work as a monomer for the further polymerization. While here, if A type of molecule there, then only this A will combine together and it will form the polymer. The molecular mass of a polymer, here I have said already, in the addition polymer, the lump sum amount of the molecular weight will be there in the after the further polymerization, while there will be some loss of the molecule in condensation polymer, so there will be some molecular weight changes will be there. Product obtained, here in the product obtained may be thermosetting or thermoplastic. Here the product obtained are the thermoplastic. For example, polyethylene, polyvinyl chloride, polystyrene. And this is the example of a bakelite polys. And the example of the condensation polymer is a bakelite, polyester, polyamide, etc. Now coming to the last classification, that is a classification based on the molecular forces. This is further subdivided into the four parts, that is the elastomers, fibers, thermoplastic and thermosetting plastic. These are the four type classification of the polymer which is based on the molecular forces. Especially here intermolecular forces are there. And now coming to the intermolecular forces or intramolecular forces. Intermolecular forces, that means the the interaction between the molecular forces between the two different type of molecule. And intramolecular forces, that means in a single molecule that interaction will be there, that will be called as intramolecular forces. That forces will called as intramolecular forces. Now, depending on the intermolecular forces, here we have already written that intermolecular forces, the polymer are classified as elastomers. Elastomers, those polymer in which the intramolecular forces of attraction between the polymer chain are weakest. Here, that weakest, it is a most important, then only elastomer will be formed. Have an and it has an elastic character. Elastic character means we can stretch and it will come to their original position. Like that, rubber are called as elastomer. So those polymer in which the intramolecular forces of attraction between the polymer chains are weakest and have an elastic character like that of rubber are called as elastomers. Because of the impending weak forces, polymers can be easily strained by applying small stress and regain their dominant shape when the stress is deflected. For example, this is the one rubber. We are pulling from the here and here, that by the forces we are pulling it, and but it should be in limit only. And when we are removing that forces, it will come their original shape, that it is known as a elastic. So the most important example of an elastomer is a natural rubber. These polymers consist of a randomly coiled molecular chain, and they have the weakest intramolecular forces. For example, Buna and neoprene, etc. These all are the category of rubbers only. Now coming to the second part, that is a fibers. These are polymer that have strong intramolecular forces between the chains. These forces are either hydrogen bonds or dipole-dipole interaction. While in this elastomer, generally the forces will be the van der Waals forces, because it is a weakest interaction. Van der Waals forces. Fibers, these are the polymers that have a strong intramolecular forces between the chain. These forces are either hydrogen bonds or dipole-dipole interaction. These polymers are long, thin, and thread-like, and can be woven into a fabric. Even though that elasticity is means it has a high tensile strength. Tensile strength means we can pull it, and if we will remove the forces, it will come to their original shape. So high elasticity properties it is having. Hence, they are used to make fiber. Common examples are nylon 66, terylene, silk, etc. These are thread forming solids and a high tensile strength and common modulus. They have a strong intramolecular forces such as hydrogen bonding and, as I have said, dipole-dipole interaction. For example, polyamides, polyesters, etc. Now last class, the part of that molecular forces classification, that is a thermoplastic and thermosetting plastics. Thermoplastics are linear and barely radiated long chain molecular component of constantly softening on heating and hardening on cooling. That means whenever we are heating that thermoplastic, they will change their shape, and means we can change their shape. And if that we will remove the temperature, or we cool that plastics, it will harden. For example, these holds intramolecular. For example, polyethylene, polystyrene, and polyvinyl. And these thermoplastic hold intramolecular forces of attraction, and that will be in between the elastomer and fibers. That means it will be not that much weak and not much that much strong also. So it will come under the intermediate between the elastomer and fibers. But this is the main point of the thermoplastic, that we can recycle that plastic many times. Like, we can heat the thermoplastic, we can change their shape, and further while cooling, it will harden that whatever we have given that desired shape, it will harden. While uh, thermosetting plastic is a polymer that irreversibly become rigid. Means whatever we are given the shape and structure, it will not be changed further when we are heating we are heating the thermosetting plastics polymers. Rigid when heated. Such a material is also known as thermoset or thermosetting polymer. In these polymer, the intermolecular forces are intermediate between the elastomers and the filaments. There is no cross-linking between the chain. Softening occurs when polymer chains move more and furthermore freely due to the lack of cross-links. Whenever cross-linking will not be there, then only it will soften. Common example of a thermosetting plastics are nylon and bakelite. Here, these are the examples of the thermoplastic and thermosetting plastic or thermosets. These can be melted. Here it is written can be melted repeatedly. That is why we are saying like thermoplastic is a recyclable plastic. Since right now whatever in the market that plastic is coming, it is written like a triangle shape, that is a recyclable. So we can further use many times that plastic. We can recycle and we can change their shape also, and we can reuse. That is why this is a recyclable plastic. While thermosetting plastics or thermosetting polymers, it will not be recyclable. Once shaped, cannot be melted. Means whatever we have given for the first time, the shape we have given, that will not be changed at all. For example, whatever utensil we are using, the handle of that utensil, it will comes under the thermosetting polymer. We cannot change their shape further and further. It will be whatever we have given the shape in the for the first time, it will be like that only. There are some differences between the thermoplastic and thermosetting plastics. For example, these are the thermoplastic is a addition. Yes, this is very important. This is the addition polymers. And for example, as I have said, polyethylene, it is a best example of a thermoplastic. While thermosetting plastic is a condensation polymerization. It will formed by the condensation polymerization. The resin are made of a long chain attracted by the weak van der Waals forces of attraction, and this resin have the 3D structure, because we are saying like a cross-linked here in the thermosetting plastic, cross-linking will be there. While we are discussing that a network or cross-linked polymer, what we are saying that we cannot change that shape further once it will be hardened. When it will be hardened, we cannot change while giving the temperature. On heating, they soften. This thermoplastic will soften, and on cooling become stiff chemical nature, that will not change. On heating, they become stiff and hard, and there is a no change on cooling. So whatever we have given for the first time, that structure will be retained again and again. They can be remolded, or we can say recyclable, and they cannot be remolded because one set means they are permanently set. It will be that waste product can be used. It cannot be used. The resin are a soft, weak, and less brittle. Because of this property only, it is a more and more recyclable. And this is usually hard, strong, tough, and brittle. These are easily soluble in more organic substances. That is why we can change their shape again and again. For example, polyvinyl chloride, polyethylene, etc. And while these thermosetting resins that are not soluble in organic organic solvents, for example, nylon, bakelite, etc. Containing that thermoplastic, it contains long chain polymers, and there is no cross linkage, while they have a 3D network. That is why what we are saying, this contain the cross linked polymer. So that's all. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.